All right, welcome back to the notes. We had to delete the first 3 minutes because we talked about nothing. Special shout out today to Haley P. Hope your teeth are okay. Lucy, hope you feel better. Nathan, we've missed you for the last 3 weeks. It's not been that long, but you know what I mean. And who else? Joe. Joe, we miss you too. Were you playing basketball last night, Joe? I thought I saw you at the golf. Maybe not. Okay. I'm convinced I saw Joe just like shooting hoops at the golf, but I didn't have time to like go check. So, crystal lattice. Do you guys remember that?
Yeah.
Yes. Ava dropped it.
Yes. It made its way onto the floor in some pieces.
Yes. And that's a great example leading to what we're talking about. Because if I drop a crystal of salt, what does it do? Salt is very what? How would you describe salt?
Brittle.
It's brittle. It's brittle. So why could we talked about this a little bit before we left. Why could an ionic solid conduct electricity? Because it has a what? A sea of electrons, right? Oh, this isn't why, this is when. Okay. Salt by itself. Can salt conduct electricity? Just like, no, it can't. If I put in a lead into a pile of salt and a lead into a pile of salt, would it conduct electricity? No, because the electrons are fixed in the solid form. How could I make those ions more free-flowing? There's two ways. You could melt it. You could melt it / make it molten. Kel said the other one, or dissolve. That's super important to know. That ionic solids, in order to make them conduct electricity, you can either melt them or dissolve them. So, great way to do it. Melt, make it molten, or dissolve it. What would that look like? Well, it looks something like this. So here's the lattice. This would be my NaCl being attacked by water, right? The positive end of water is going to attack the negative end of the lattice. Here's a hydrated anion. Look at that. Doesn't that look kind of creepy? Yeah, I know. It's kind of creepy. Here's a hydrated cation. It's just the other side touching it. You got it. Ionic solids are polar, for the most part. Polar means they have, how is their charge inside of it? Positive and negative. Also, evenly or unevenly distributed? Uneven. Remember, polar means there's poles. The polar molecules on page 308 are attracted to oppositely charged ions. What was I thinking about on page 308? Oh yeah. Remember all these pictures? Yes? So this was non-polar down here. This was polar. Yes. Over here. Would this be polar or non-polar? Polar. It's not evenly distributed right here. Up here, polar, non-polar, polar. You got it. You got it. Are attracted to the oppositely charged ions. This is the idea of like dissolves like. So have you guys ever heard that before? Okay. Well, now you have. All right, like dissolves like. What does that mean? That means if something is polar, it's going to dissolve something that's polar. Water's polar, salt's polar. Do those dissolve in each other? Yeah. Yes. Is that why, though? No. It's because water has a positive and negative end, and so does salt. Water and oil, do those dissolve? No, that's because water is polar and oil is non-polar. So could you use like dissolves like on an AP test? No. You'd have to understand actually what's happening beyond that. Did you guys all get muffin or Rice Krispie? Okay. Whoa. Do you guys like this shirt? It's new.
Yeah.
It's like kind of waffly, like people that aren't here, here's what it looks like. Yeah. That's so funny. I always wonder if like random people on YouTube find these notes somehow and they're like, who is this guy? Because you never see my face.
There's one fan out there.
There's got to be one.
A loyal fan.
Got to be one.
Can you see how many views you get on it?
Oh yeah, it's like 4.
Oh.
It's literally just people that miss the notes, which is fine.
I go back and watch them. They're good notes though.
Yeah, I now have several people like in college that are going back and watching them. Because like if you need something. I was talking.
If something funny happens, I'll just go back and like watch it.
Yeah, it is good.
Like you look back on them.
Yeah, I was actually messaging Emily Hammond and Tyler Hamilton last night because they're in Chem too, and they're like, our Chem professor just explains it way more complicated than it has to be. So, because Emily and Tyler both go to Toledo, They both got out of Chem 1. They're in Chem 2, but it's still stuff we've covered. So, it's, yeah. AP Chem really covers the whole first and second semester of college. So, yes. This process is called hydration. This process is called hydration because the ions are now said to be hydrated. I know. Mind blown. Hydrated. Now the ions are free to move, so it's a great conductor of electricity. If a non-polar solvent was used, nothing would be attracted to the ions due to no dipole moment. Remember talking about dipoles. What do we do for dipoles? Dipole. Yes. So the ionic bonds would not stay solid and not dissolve. Not dissolve. Also, that was one big run-on sentence. If you look at that, there's like...
It starts at now, I think.
I think it's right here. If a non-polar solvent was used, like that's one big sentence.
Okay.
So the hydration process increases the, what we like to call entropy. We're going to talk about that more in like March of the system. Entropy is disorder. Entropy is disorder. Flip the page. Flip the page. In the simplest terms, you could think of compounds being 100% ionic, which would be polar, or 100% covalent, which is what we've talked about up to this point. Imagine me trying to teach my freshmen this, okay? But these situations are only at the extremities of a sliding scale. So it's really a sliding scale. What was our true ionic example we talked about Friday? Francium and fluorine. Most reactive metal with the most reactive non-metal. By the way, most of you got that bonus right on the test. Oh, shoot. Well, that's not. That didn't really give it away. All the way. Anyways, it's true. And then what were our pure covalent bonds?
Oh,
Diatomics. Yes, because they literally have the exact same what? Electronegativity. The actual types of most bonds are intermediates between the two, with a largely covalent substance having some ionic behavior or vice versa. This majority group of compounds are called what? We talked about this. Polar covalent. Polar covalent. I know. It was on the tip of your tongue. So, point of this whole thing is to understand what ionic is, what covalent is, but know that most compounds are neither. They're both. They're polar and they're covalent. Okay. Get out your regular paper. Just regular papel. Papel? Did I say paper? Does that sound right?
How do you say little bird?
All right, this next thing I have to draw is hard, just to let you guys know.
Are you going to engineering?
No, this is interesting though. More ionic compound stuff. So I don't really have like an official title for this. We'll call this more ionic compound. Everything's ruined. We're done. Just kidding. I know you guys would be so happy about that. I think I just like unplugged.
See you now.
You're right. There has been some cameos made.
Or you like.
They saw my shirt though. Well, now I might as well show the outfit. Like fit check. See, like look at this shirt. Like isn't this like kind of? Yeah. What's that thing on Roblox? Pose. Yeah.
Where's the chain from?
This chain?
Yeah.
This is from Swivel. Yeah, Fit Check. Fit Check is Old Navy, $5.99. Jeans probably from Kohl's. Shoes are Brooks, running shoes.
Oh, that's the shirt.
Yeah. The shirt underneath, Worcester High School, something. Worcester High School something. Oh, and also Bomba socks.
Oh. Hey.
Bomba socks. Every pair you buy, they donate a pair. So, there you go. And they're really comfortable. And they're lifetime guaranteed. Wow. We've literally just had a commercial for Bomba socks in these notes. I feel thankful for that. Bomba, if you are listening, please sponsor AP Chemistry, Worcester High School. 515 Old Mill Road. What? Lifetime warranty, yes.
I feel like that's not even worth the price of those socks.
They're so high quality, they don't have to usually replace
They
them.
are.
Oh, really?
Yeah. Anybody here wear Bombas?
Yeah.
Okay.
Dude, I need to get one.
Ask for a pair for Christmas. It will change your life.
They're nice.
They're nice. They're nice. Okay. All right, you're going to want to skip about halfway down your page. All right? We are going to be drawing a little scale on my y-axis. It's not really even a graph. This is going to be energy in kilojoules. And what we're doing here, this is called I haven't even left myself in the room already. This is called the Born-Haber process. The Born-Haber process. The Born-Haber process. Also, essentially, how a molecule forms. How a molecule, M-O-L-E, that's a C, can you guys tell?
Wait, born what process?
Born, B-O-R-N, Haber, H-A-B-E-R, process. I'm using a very fine tip pen today, which is making it difficult to write with decent handwriting. So, when we put my example is going to be lithium and fluorine, right? Yes? Lithium and fluorine does form lithium fluoride, agreed? It would really want to, right? Lithium wants to do what with one electron? Donate. Fluorine wants to do what with one electron? Get it. Yes, I appreciated that. Yes, yes. So here's the process. I'm going to start down here. So down here at the bottom, I have lithium, which is a solid. Lithium, which is a solid, plus 1/2 F2 gas. So I have lithium solid. So I have solid lithium plus a 1/2 mole of diatomic fluorine gas. 1/2 mole of diatomic fluorine gas. What is going to be the first thing that I have to do? So I'm going to put a little line here. All right. I'm going to put a little line here, and I'm going to draw a little arrow up. Any guesses of what I have to do first in order to make this combine? I've got a solid and a gas. Change something. What? Which state of matter am I going to want to change? Probably the solid, right? Can I make a gas and a gas interact more easily than a solid and a gas? Also better than a solid and a solid, yes. And if I turn lithium directly to a gas from a solid, so now I have lithium gas, still plus 1/2 F2. And don't worry, you guys don't have to memorize anything like this, but I'm just showing you the process. What would that be called? This energy that I just used, solid to a gas. Solid to a gas. Sublimation, yes. This is the energy of sublimation. So let's say that this sublimation energy is 161. It took 161 kilojoules to do that. Okay? Now I have lithium solid and I have lithium gas and I have fluorine gas. Let's take that up a little bit more. All right? The next thing I'm going to do is I'm going to turn lithium into its ion. It's ionic form. So now I have lithium ion, which is the gas, still plus 1/2 mole of my fluorine gas. What did I just do to lithium? Ionization energy. You got it. This is the ionization energy. I ionized it. This is the whole process of this whole thing happening. And let's say that that is 520 kilojoules. I don't know why I said 520 like that. If you pronounce your T's, you sound much more sophisticated.
I don't think so.
I do think so. Why don't you think so, Ava?
You're just making every word
It
sound.
sounds like it's.
But if you really think about your T's,
You're a robot.
you may sound more sophisticated.
It's more proper.
Yeah, you just sound more, I don't know. Hey, have you guys seen my shirt? That's how my brain is right now. Like, I'm really trying to focus. I know, we gotta keep going. I know, we should, but we have to keep going. This and one more thing is what I want to get through. We got this. We got to keep going.
Yeah,
I don't know if we'll have time.
I support getting picked.
It's just
The less hard we work today, the more hard we have to work after break. So it's just like, we need to find that happy
I'm already
medium.
on break.
We're missing one.
I'm already on break.
All right, I know you are. I know. Okay, last step. Let's go up to here.
We should do
I now have lithium ion, which is a gas, plus I don't want a half mole of F2, I just want regular fluorine gas. So now I'm ready to create a bond. So this is my bond energy, which we're going to talk about more. Let's say that's 77 kilojoules. So I now have lithium gas, ion plus fluorine. So I made it to the top. I'm going to go over here. And now I'm going to start going down. So I'm going to start going down. I know. I hope you left enough room for this.
I did not.
I'm sorry about that.
Any of this, let me tell you.
I have lithium ion, which is a gas. And now, what does fluorine want to do with one electron? Wants to gain an electron. Okay, if fluorine wants to gain an electron, what type of energy would that be called? Which trend? Electron what? Electron affinity. Yes, same thing, right? So this is the electron affinity energy. See how I said that's so pronounced? Now my matter is getting more stable. If my matter is getting more stable, I'm going to start releasing energy. Negative 328 kilojoules. So I'm releasing that much energy. I have almost formed an ionic compound now. My last one is my biggest jump. What is the last thing I'm going to do to make this a true ionic compound? When it becomes ionic, what special structure does it have? We talked about this yesterday. I passed it around. Ava dropped it. Lattice. Yes. This is the lattice energy, this last jump. Yes. We always remember lattice energy with Ava dropping it from this point forward. Lattice, L-A-T-T-I-C-E, energy. It's like lettuce. Well, not really, because lettuce is U. It's not L, actually. Let's say that this is negative 1047 kilojoules. So, anybody have a guess? So I'm ending up down here. Anybody have a guess what the distance between where I started and where I ended would be right here? The distance between those two?
like 500 kilojoules.
Yeah, but what would that represent? Delta H reaction. That would be my heat of enthalpy for the whole reaction. Do you want to add it up, or do you just want me to tell you what it is? All right, if I add all these up, right, this would be negative 617 kilojoules. So, on a test, super easy, all you have to do to figure that out is delta H reaction is equal to sublimation energy plus ionization energy plus bond energy plus electron affinity plus lattice energy. You literally, I just kind of made that a lot to show you to just add them up. Now, here's what you have to do on a homework problem. They're going to say that it is, I don't know, like half the ionization energy. So you'll have to take your ionization energy and divide it by 2. Or they're going to say it's 2 moles of electrons being given away. So you might have to multiply electron affinity by 2. Something like that. So it's literally just adding them up to a total, and you have to figure out what you have to change.
So do they do, wait, do they give you like all the, did you get?
You'll be given everything. But they're just going to say 2 moles or 2 electrons, and you have to figure out which one to divide or multiply by 2.
So
Yes.
they'll only change one thing.
Most likely.
Are we
Yep.
always getting like the stuff on the side?
What?
Are we always
Yeah.
gonna get, like, the-
Oh, yeah. Yeah, you'd be given like a list. You'd get all these things, and you just have to figure out which one to multiply to, which one to divide by 2. Or I could give you this and then solve for x. You've done that like 4 times now. Cool? Once again, let's talk about lattice energy, and we'll move on from this. Lattice energy, we're not even writing out energy, is the energy required to separate a mole of electrons I guess, well, or let's not even say electrons. A mole of an ionic solid, into gaseous ions. So the energy required to separate a mole of an ionic solid into gaseous ions. So which one of these would have the higher lattice energy? So the higher lattice energy. Would it be CAF, or MGF? You gotta think about it for a second. Kel's positive that's CAF. Anybody want to go against her?
No.
Audrey?
I want to go MGF.
I feel like it would be MGF because there's, well, with MG, you're closer to the nucleus, aren't you? So it would be a bit more difficult to separate up the electrons.
Coulomb's law, right? Calcium's charge is +2, so is magnesium, agreed? Fluorine is -1. Charges are the same, right? So then I have to go to distance. The ones that are closer together are going to have the higher lattice energy. Because magnesium is a little bit smaller than calcium, that's going to have the higher lattice energy. You okay with that? Yes?
Where's that word saying solid?
Ionic into? Yeah, ionic into gaseous ions. Yeah. Did you bring your book today?
There is no O there.
Do you have access to the online book?
I got a book.
Okay, or have a partner that has a book? We need at least one book that per 2 people to do this next thing. I forgot to tell you. So find someone that has a book or open up your online book. So we're talking about bonds.
I'll just use my brain.
I think I can fit the rest of this. Yeah, I'm just going to flip the page. We're going to talk about bond energies. Bond energies. What? I do. So I'm going to write a compound, and then we're going to draw out what bonds this would be. So I have CH4 plus O2. What type of equation am I writing right here already? I already know this is what? Combustion. That gives me CO2 plus what? H2O. Is that balanced? No, it's not. So let's put a 2 here and a 2 there. Is that balanced? Okay. So I would ask you, that's balanced, isn't it? 4 O's, 2 plus 2 is 4 O's, 4 H's, 4 H's. Okay. I would want to know what is delta H reaction for this. So delta H reaction equals what number? So this is similar to what we were doing with our delta H reaction for the heat of enthalpy, but this is now bond energies. So what would CH4 look like? C, H, 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 H. Agreed? Yes? Diatomic oxygen has what type of bond? Double bond, right? You guys remember doing that? We already did carbon dioxide, right? Carbon, double bonded oxygen, 2 lone pairs. That was from Friday. And then water looks like this. Water looks like this. Does that look good? Now, I've got 2 of these, and I've got 2 of these. Open up your book to page 323. 323. Or your online book to page 323. Yes? Yeah, there's cups over by the window, by that big beaker. Why are you getting a hot chocolate? Okay. Let me make sure you have spoons, too. Page 323, chapter 8 or chapter 9. No, not those. These. Here's spoons.
What? You're gonna put hot chocolate on a plastic.
Here. There we go.
Grady's
Did
on
you find
break
it?
right now.
320. Did you?
It doesn't
It's
have-
like a chart.
Search.
It's a chart of bond energies. Did you find it?
Right here.
Oh, search.
You just wanted water?
Keep going. Keep going. Wait, a little lower.
I'm so confused by Grady now.
Okay, flip it one over.
I'm gonna grab a coffee.
323.
Oh, you need that.
Maybe it's one before that.
Yeah, it's like one behind.
322. What's that? Go down a little bit. Yep, 322 on the online book. Okay. We can always brew another pot of water if we have to. Okay. So, a new form of delta H reaction. Delta H reaction is going to equal the sum, does this look familiar? Of the bond energy of the broken bonds minus the sum of the bond energies of the formed bonds. Does that make sense? Bond energy. Think about that. Which bonds am I B, bond energy, broken, minus bond energy formed? Does this make sense?
How would it be bond energy formed minus?
Well, it's a great question. So in the past, we've done products minus reactants. Yes? Which one of these do I have to put energy into to make happen?
To break bonds.
To break the bonds. And when I form the bonds, they're becoming more stable. So that's releasing it.
I see. So
That's why.
when it's formed, it's negative.
Yes.
So technically it's gonna end up being zero.
It just helps your numbers be the correct. You got it. Yep. Helps your numbers be the right positive or negative. You got it. Depends if it's endothermic or exothermic. But I'm breaking the bonds in my reactants and I'm forming the bonds in my products. Okay? So everything we've done so far has been products minus reactants, but for bond energy, this is technically reactants minus products. This is not hard, but it's one thing that people get confused on the AP test. It's super easy. So let's do it. So delta H of this reaction is going to be how many bonds am I breaking and how many CH bonds am I breaking? I got 4 moles of C to H, single bond, right? Do you guys see how I'm breaking 1, 2, 3, 4 of those? Does that make sense? Head nod if that makes sense. And what is the bond energy for carbon to hydrogen? On page in your book. 413. So 4 moles times 413. This is still kilojoules per moles. Plus, right? This is a sum. How many oxygen double bonded to oxygen bonds do I have to break? 2. So I have 2 moles of O double bonded to O times, what is the bond energy of O double bonded O?
495.
495. Yep, that looks good. Times 495 kilojoules per mole. That's my reactants, yes? Minus bonds formed. So bonds that I formed. Are all of these bonds new? Is the first question we have to ask ourselves. Did I have any C double bonded O on the left? No. Did I have any H single bonded O on the left? No. Sometimes you're not forming new ones. Some might stay the same. So you really have to look at and see what you have. Because if you have one that doesn't do anything, are you going to include that in this equation? No. But this one they all do. So minus, how many C double bonded O's do I have? I've got 1 here and 1 here, right? So minus 2 moles of C double bonded O times, what's the bond energy for that? Now, look at the little asterisks. Do you see an asterisk?
Yeah, I do on the.
Right, I just want to make sure people see that. Do you see how there is C double bonded O? But the asterisk says in CO2, it's what?
799.
Because that makes sense why it's 799, everybody. Yes. I gotta see a head nod. On the chart, it says 745, but do you see the asterisks on the chart? Yes. And then below the chart, it says in CO2, it's actually 799. Are we okay with that? Yes? Okay, now I see head nods. Well, because in carbon dioxide, we're gonna learn next chapter, there's just different intermolecular forces, which changes it a little bit. It has to do with the bond angle and intermolecular forces. Times 799 kilojoules per mole. So there's my first ones out of form. Plus, how many H single bonded O's do I have? No. No. 4. Plus 4 H single bonded O. Right? Because I've got 2 times 2. Agreed?
So shouldn't the one before that, 2 moles, is that 1 mole?
I've got 2. I've got 1, 2. Because carbon dioxide has 2 of those.
Okay, even,
I only have 1 of that. 1 times 2 is 2. Here I've got 2 times 2, which is 4.
oh, okay, that makes
Okay? So 4 moles of HO. And what is HO? Ho, ho, ho. 467 kilojoules per mole. So add that up. And that will give you your delta H reaction.
You could put that in the calculator.
Huh?
So when you're putting in the calculator,
You do 4 times
4
this
times that. So
plus
would it
2
be
times
4?
this equals,
Would it be 4 times 4?
it'd be 4 times 413.
Oh, that's 413. That's
413 plus 2 times 495 equals, minus parentheses, 2 times 799 plus 4 times 467 and parentheses equals. Make it do order of operations. Anybody doing it? Joe's doing it. He's got us. Joe is our master mathematician. I love it. We trust him.
We trust it.
Henry's putting it into Desmos. Listen.
Full face of credit.
It's like a race.
Negative 824. Do we have a confirmation?
I did not get that, so hopefully you guys.
What? Do we have a second? Yeah, it should be negative 824. What? Kilojoules. So what's my delta H reaction? Negative 824. Negative 824. All right, can I give you just a preview of where we're going on after break?
Sure.
I promise we won't take any more than the space you have left on your page. Where are we going? Great question. This is going to be my introduction to bonding structures. Here is the thing about what we're about to start. This is like the second chapter of this chapter.
Wait, so are we starting our notes right now?
We're continuing the notes. All right? This next thing depends. Who would say they are a visual thinker in their head? They can visualize things in their head. Raise your hand high if that's you. Some people. Raise your hand if you're not a visual thinker. Okay, mid. Because if you're a visual thinker, you're going to be able to like visualize a lot of these things. If you're not, you're just going to have to memorize what we're doing. Which either way, it's not a big deal. Because you'll see when we get to the end of this what I mean by visualizing versus memorizing it. So let's look at CH4. CH4. What's bonding here? What's bonding to what? Would you say C is bonding to H or H is bonding to the C? I would say H is bonding more to the C, right? In a way. Yes? So CH4, let's do my outermost electrons for carbon. So carbon would have my 2s electrons. Agreed? Are both of those full for 2s? So that's going to be an up-down. And then carbon actually also has, here's my 2p electrons. What does carbon have for my 2p's? Does it have any? It has an up and an up. So hydrogen has how many electrons to share? Could I put one down electron here, right there? I could. That's one hydrogen, right? Could I put one hydrogen here, a down electron there? Could I pair there? This isn't going to work. Agreed? Because I got a pair. Yes? Any guesses on what I could do to change this to make room for 4 hydrogens to bond? Yes?
You could take the electron from the 2s.
I could promote an electron. That's exactly what I'm going to do. I'm going to take this electron here, and I'm going to promote it to here. And now it's spinning up, right? So I have promoted 1 electron. Now, is there anything technically here? No. So now what's going to go here? Do I have room for a down H here? And now do I have room for a down H here? Yes, I do.
Are all H's always down?
What?
Are they always spinning down?
Not necessarily, but in this example they are. All right, I'm just trying to give you an example here to show you what you do here. Guess what I've just done? Guess what you've just done? You have just hybridized your first orbital. You're hybrid now.
Hybridize?
Yes, you have just hybridized your first orbital. How many orbitals do I now have hybridized? Is my s orbital hybridized? Are all of my p orbitals hybridized? So you're telling me that I have an s orbital hybridized and all 3 of my p orbitals? That's sp3 hybridized. Because I hybridized 1 s orbital and all 3 of my p's. You guys okay with that? Danny?
Why is there an arrow on the ceiling?
An arrow? That shows how the HVAC moves if they need to work like up in the ceiling.
That duck picture always been there.
The duct picture's always been there.
It literally just got rid of that.
You think so? Also, I think we should change that to Mr. Ruff leaving on the hate list, because I've had a lot of questions. Like, do you guys hate Mr. Ruff? Like, no.
No, we love him.
But we should say Mr. Ruff leaving instead of like Mr. Ruff,
We should
the
make
person.
it into the dean of students job.
Okay. So, S orbital looks like what? Do you guys remember the shape of an S orbital? Sphere. Remember the P orbital? Dumbbell. Dumbbell. Any guesses of what an SP orbital looks like?
For a snowman.
Yeah. Not like a snowman, but kind of like that. All right, it's kind of like, you got it. You got it. Now, what if I tried to draw these orbitals, right? This is going to be really crazy. So, if I was going to draw this, I would have, I'm going to try to draw this really well.
Wait, put down your paper.
Oh yeah, my bad. My bad. Okay. See, I'm not good at visualizing this, so I have to actually think about this. Okay. Okay, there's one sp orbital. Okay.
Let's get the car.
Here is it's fine. Another sp orbital.
Okay, you know, why is your left arm like non-existent?
I've been looking at that old class.
What are you talking about?
On the picture behind you. Accurate representation of material.
I don't know. It's freshman. It is hard to focus. I agree. And then I've got one more. Here's like the little piece here. Go into there. It's hard to draw this 3D. All right? Do you see this shape? All right, you have to be able to kind of visualize this.
I'm getting it.
All right. Oh, I need to have one more because there's 4, right? There's 1, 2, 3, 4 orbitals. So I also have to draw one kind of coming, here's one going this way, coming out this way. Okay?
Beautiful.
I'm getting it.
All right? So I've got 2 shapes here, right? I kind of have Do you see how there's kind of like a trigonal base?
Yeah.
But there's also like a pyramid going up.
Oh.
It's hard to see. It's hard to visualize.
Not supposed to be the center?
What? This is just not really. I more just care where the electrons are. Do you see how there's like a trigonal base? Yes. So there's a trigonal base. Plus there's one rising. So it's kind of like a triangle square. If I was going to draw like this, it would look kind of like this. I can't draw 3D. And then there's like one coming up here, kind of like that. Look at that.
This is I thought I had it on.
I think it's supposed to be up here.
Any
It's like a triangle. base.
any guesses of what this shape would be called?
Triangle. A pyramid.
Tetrahedral.
Tetrahedral. How'd you know that?
We were talking about that the other day.
Ah, this is tetrahedral. This is tetrahedral. That's tetrahedral. It's a trigonal base plus one rising.
All right, I'm ready for a hard one now.
No, we're out of time. All right, that's a good intro to where we're going with this next. Good intro to where we're going with this next. Plus, I don't want people to have to watch too many notes every week. That's a good preview of where we're going next. Stay tuned for Vesper and bonding.